Magnetic flux. I've made a very sophisticated, hi Dewan, a very sophisticated simulation here. We've got a magnetic, two magnets. So it's a uniform magnetic field inside. It will, as it is with electrostatic capacitors, it will bend around the outside, but we're ignoring that for the moment. We're really only interested in the magnetic field inside between the poles. So when we did electrostatics and capacitors, we had something like this: positive, positive, negative, 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 and we looked at a little positive charge there, and it raced along there, and we were interested in the electric field because we said the force is equal to the charge on, so the electric field is equal to the force on a charge, and we looked at electric field as volts per meter, and it worked. But when it comes to electromagnetism and inductance, the electric field is not so important. The magnetic field not so important because, hi Narito, it's not so important. Something else is important, and what's more important in this case is flux. And the reason is, hi River.
Hi, sir.
Welcome, welcome. The reason is because of electric motors and generators and inductors and circuits, which we'll come on to in a week or so. And here we've got, between our north and south pole, we've got a magnetic field, and that magnetic field in this case is constant. It's constant. It'll be however many Tesla. 1 Tesla is really huge. And into this magnetic field, we have a loop of wire. And this is my really sophisticated simulation. Is that clear enough? Can you actually see the wire there? I mistakenly chose white wire.
You can see it.
Okay. So when my little loop cuts across the magnetic field, then I've got a certain amount of magnetic field passing through it, and that magnetic field is constant. We're not going to change it for the moment. But as I rotate my coil, when the coil is flat like this, there is no magnetic field through it. So simply by rotating our coil through a quarter turn, through 90 degrees, through pi upon 2, I've changed the amount of magnetic field that's passing through it. And changing that magnetic field through this loop induces an EMF. It induces a current through this loop. The magnetic field is constant. Unlike our electromagnetic field, our electric fields, where we're very interested in the size of the electric field, when it comes to magnetic fields, what we're interested is the amount of magnetic field that goes through our surface, through our loop. And the amount of magnetic field through the loop is measured in flux. And flux, as you saw in beginning the notes, magnetic flux is equal to the magnetic field strength times the area. So with my little loop here, what's the flux in my little loop here? Close Eva. What's the flux through my loop? The flux is the magnetic field strength B times the area of my loop. That's the amount of flux going through there when it's at a right angle to the field. When I rotate it through 90 degrees, through a quarter turn through pi upon 2, now there's no magnetic field going through it. The flux is now 0. So we've actually had a change of flux, and changing it, as we see, changing this induces an EMF in it. So what we're interested in is not the change of magnetic field, but what interests us is the change in magnetic flux. So flux is the much more important variable than magnetic field. So we say the magnetic flux is equal to the magnetic field strength times the area of our loop or whatever. And the magnetic flux has got its own unit, and its own unit is Webers. Weber, capital W, little b, magnetic flux. And another, so this is the flux is what we're going to be mostly concerned about. And if we divide flux by area, we get flux density. So that's going to be Webers per square meter divided by area. And flux divided by area is equal to magnetic field strength. So magnetic field strength we can describe as flux density, Webers per square meter. So a Weber per square meter, if it's equal to the magnetic field strength, is Tesla. So Tesla, our unit for magnetic field strength, is Webers per square meter. So coming back to our point, magnetic flux is equal to the magnetic field strength times the area. Magnetic flux through my loop at this point is equal to B times A. My flux when my loop is at a right angle to the field is equal to B times the area of my loop. Okay, first point. And then from there we go to voltage, induced voltage in an inductor, in a wire, in a loop, the induced voltage, and we will get an induced voltage as we rotate this loop in the field. As it rotates in the field, the magnetic field, the magnetic flux changes and we get an induced voltage through our loop. And our formula for that is the voltage induced is equal to the rate of change of flux, rate of change of magnetic flux. That's why flux is important, more important than magnetic field strength. And because it's an induced voltage, it'll be opposite to the applied voltage. So we have a little negative sign in there as well. So the induced voltage is equal to the rate of change of flux. we can show that if we want to, but you can look it up yourself somewhere. So let's have a look at a problem then. And I found a problem in the book that I thought was quite a good one, really. There we go. Here's our problem. The problem is we have a circular wire inside a magnetic field, and you can see there's points there. So what's the direction of the magnetic field? Magnetic field is up out of the page. So we've got a loop sitting happily in a magnetic field. So some of this magnetic field passes through the loop. So we could consider the flux, the magnetic flux through the loop. So number one, the diagram shows a circular coil of wire of area 0.1 square meter. So A equals 0.10 square meter. And a magnetic field of strength 0.80 Tesla, which is a very large magnetic field. The magnetic field is then reduced to zero during a time of 0.40 seconds. How much flux initially passes through the coil? So magnetic flux is equal to the magnetic field strength times the area. The magnetic field strength is 0.80 Tesla times area 0.10. So the magnetic flux 0.1 times 0.08, 0.080 Weber. Okay, how much flux initially passes through this loop? Magnetic field times the area. That's how much magnetic field we've got to play with. Amelia, Mario, does that seem right to you? The amount of magnetic field that we're dealing with? I turn to you, Mario, when it comes to electronics because of your brilliance at that, right? Let me just, I'll just take a interlude just to finish the roll. Duncan, you're here. Welcome.
Hi, sorry, I got you 5 minutes late.
That's quite all right. It's nice to have you here. Very nice to have you here. Okay, I've got everybody. Wonderful. Okay. How much flux initially passes through that? 0.080 Weber. Two significant figures. What is the size of the induced voltage in the coil as the magnetic field strength is reduced? The voltage is equal to the rate of change of magnetic flux. So the change of magnetic flux, when the field is reduced to zero, the change of magnetic flux is it starts at 0.080 and comes down to zero. So the change in magnetic flux is 0.080 Weber, and the time taken, it took 0.4 seconds. So that means we've got a voltage of 0.2 volt. So that's the voltage which is induced in that coil when that magnetic field disappears. 1, 2, 3. The slightly tricky bit is what's the direction of the induced current? So as this magnetic field disappears, there'll either be a current going this way or a current going this way. And this is where we depend on Lenz's law. Lenz's law says the induced voltage opposes the change in magnetic field. The induced voltage, the induced current will resist the change. So if we've got a magnetic field sticking up out of the page. When this starts, the magnetic field sticking up out of the page, it's disappearing. It's shrinking down. So what direction must the induced magnetic field be to compensate for that? It too must be sticking up out of the page. The magnetic field initially is sticking up out of the page. It's slowly disappearing. The induced current, the induced voltage, will set up a magnetic field that resists that change. So it will try and prop it up. So the direction of the induced magnetic field is coming up out of the page. So we can use our right hand grip rule to say the induced magnetic field must be sticking up out of the page in the center of the loop, in the center of our coil. So the current must be in this direction. So the direction of our current is anti-clockwise. So get that. What's the direction of the induced current? The induced current is in such a direction that the magnetic field produced by it opposes the change in the external magnetic field. And the external magnetic field is sticking out of the page and it's trying to disappear to nothing. To oppose that, the induced current must be trying to generate a magnetic field in the same direction to keep it sticking up. Again, right-hand grip rule. The magnetic field is coming up through our loop. Therefore, the current must be going anti-clockwise. And you can do that anywhere around the loop. The magnetic field is coming up through the center of the loop. The current must be this way. Lenz's law. B, and we'll just finish this off, and if there's any questions, I'll answer them, otherwise we'll disappear. B, with the magnetic field strength back to 0.8 Tesla, the coil is now rotated a quarter of a turn about the vertical axis. So that's the same as we had before with my little rectangular coil. It's rotated a quarter of a turn, rotated a quarter of a turn. So now the magnetic field is staying the same, but the flux is changing because the angle of our coil is changing. So initially we've got all of the flux coming through the loop, and when we rotate it a quarter of a turn, now none of the magnetic field is going through the loop. So we start out with maximum flux, and as we rotate it, we move to zero flux. So the first question, the magnetic field is changing. The second question, the area is changing. In both cases, what's changing is the magnetic flux. That's why flux is more important again than magnetic field strength. So second part, with the magnetic field strength back to 0.8 Tesla, the coil is rotated a quarter of a turn. The average induced voltage during this time is 0.4 volt. 1. What is the change in flux through the coil during the quarter turn? So the flux initially is equal to the magnetic field strength times the area again, magnetic field strength 0.80 times area 0.1. It's the same as we had before. The initial flux is 0.08 Weber. What is the change in flux during the coil? The initial amount of flux is 0.080. As we rotate it to a quarter turn, the area becomes zero, so the final flux is zero. So the change of flux is equal to 0.08 Weber. How long does it take the coil to do the quarter turn? So this is where we resort to our equation. The voltage is equal to the rate of change of flux divided by time. and we're told that the voltage is 0.4. We're told we've worked out the change of flux, so we can rearrange this equation to find the time. So rearranging it to find the time, we get the amount of time is equal to the change of flux divided by the voltage. The change of flux was 0.080. The voltage is equal to 0.4. So the time is equal to 0.2 seconds. It takes 0.2 seconds for this to turn around. And again, we could work out the direction of that current doing the same as before. So that's using our Lenz's law and Faraday's law. Lenz's law gives the direction. Lenz's law gives the direction of the change, and Faraday's law gives the size of the induced voltage. Just one last thing before we move on. I don't think it's clear in the notes at all, even if it's there. But from Faraday's law, the voltage induced is equal to negative. It opposes the voltage. Change of flux divided by time. But what if we don't just have one loop? What if we've got several loops where the wire goes around and around and around several times? What if there are n loops? N loops in our coil, then the voltage becomes negative n times the rate of change of flux. Okay, so I think that those are the key points initially in this week's study. The first day is just revising stuff from year 10, and the rest of it is this. What have I got there? I'm just going to stop recording that now. Okay, so
That's all, folks.